Today we're going to look at polygons. We're going to look at what types of polygons there are, the different names of the polygons, what an equilateral, equiangular, and regular polygon is, different types of triangles, and then symmetry in polygons. So we're going to talk about all those things, all three of those things in this video. So a polygon is a plane figure, which means it's just on a plane. It's not a 3D figure. Made of 3 or more segments such that each segment intersects exactly 2 other segments, one at each endpoint. So let me illustrate what this definition means. So let's categorize these things into polygons and not polygons. And let's refresh our memory on the definition. It says a plane figure made of 3 or more segments such that each segment intersects exactly 2 other segments, one at each endpoint. So we're talking about something like this. Each segment intersects 2 other segments at the endpoint. So this one is pretty close to a polygon, but this segment up here only touches one other segment. So this is not a polygon. This one is a polygon. Each line each segment touches each other segment at the endpoints. This one would be a polygon. This one is not a polygon because the segments are curved, or so they wouldn't be segments. This is a curve. Same thing with this guy. This is not a polygon. We have to have nice straight segments. This one is not a polygon. So basically, it's got to be a closed figure where all the endpoints are connected. So this one is a polygon. This one is 2 polygons put together, but the shape itself is not a polygon. Wait, well, yeah, this would be 2 separate polygons here. And then this one here is a polygon, it's a triangle. Okay, so let's look at the parts of a polygon. These are the sides, that's what we refer to those. Whoopsie, I'm sorry. And then the vertices. So I'll be referencing the vertices, which are like the corners, and then the sides. All right. So if it has 3 sides, we call that thing a triangle. Now, and most people know, you learned that very young. Now, 4-sided shapes, most people call a square, but that's one specific type. A 4-sided shape is actually called a quadrilateral. So a square is a type of quadrilateral, and in another video you'll look at the quadrilateral hierarchy, but there's lots of different 4-sided shapes. There's squares, rectangles, rhombuses, and so on. 5-sided shape is a pentagon. The one in the Washington, D.C. area is a very famous pentagon. It's called the pentagon. A 6-sided shape is a hexagon. 7-sided shape is a heptagon. I've also seen it called a septagon. Heptagon is the one that we're going to be using. 8-sided is octagon, 9 nonagon, 10 is a decagon, and then if it just has n sides, so say it had 23 sides, we'd call it an n-gon, or if it was 23 sides, we'd call it a 23-gon. So you don't get too clever past 10. So if it's a 13-sided shape, we just call it a 13-gon. So very, very good, clever stuff there. Okay, then there's types of polygons. An equilateral polygon is where all the sides are the same length. And we'll look at an example of this shortly. So equilateral just means all the sides are the same length. Equiangular means all the angles are the same measure. And regular means both of these. So if it's equilateral and equiangular, then it's regular. So all sides and angles are the same measure, so equilateral and equiangular. Alright, so here's a picture to kind of illustrate what I'm talking about. Equilateral means all the sides are the same. So in this case, all the sides are 2.5 centimeters. But you can notice that not all the angles are the same. This one's pretty close to 90, maybe about 95. But this one's much bigger than 90, so probably like 120. So you can have a polygon where all the sides are the same, but the angles are not the same. And likewise, all these angles are 108, but not all the sides are the same. You can clearly see that this side is longer than this side. But a regular polygon means all the sides are the same, and all of the angles are the same. So in a five-sided shape, all of the angles are going to be 108. So it'd be 108, 108, 108, 108, and 108. And then all the sides, if you measure them with a ruler, they would all be the same. So this is just kind of a picture illustrating these definitions. Okay. And then in particular, there are different types of triangles. So for triangles, this one, where all three sides are different, this one's called scalene. This one has no equal sides. The one where there are two equal sides, so just these two sides are the same, but this one's different, this one is called, oh, let me see if I can do this. This one's called isosceles. And then if all three sides are the same, we call that equilateral. And that's a regular because all the angles are going to be the same as well. So in a triangle, if all the angles are the same, then all the sides have to be the same. That's the only polygon where that is true. You could have a polygon where the angles are the same but the sides are different, but not in a triangle. Okay, so let's look at symmetry then. So an object has symmetry if it looks the same after being rotated around a point or reflected over a line. So let's look at these and determine which ones have symmetry. And so this one has reflective symmetry if we take and we cut it right down the middle, like so. If we folded it, this bottom side would match up identically to the top side. So this has reflective symmetry, and this here is our line of reflection, that line I drew in there. This one has rotational symmetry if we turn it. So if we take this shape and turn it, it'll line up with itself. And so let me see if I can do this. I'll try cloning this. Oh, that's not going to work very well. I'll just delete it. But if you rotate it, this one, we'll number these. We'll call this one 1. Let's see, 1, 2, 3, 4, 5, oops, 6, 7, and 8. So if we rotate this thing, the 1 will match up with the 2, and then the 2 will go to the 3, and the 3 will go to the 4, and so on. So this thing is said, and what our book uses, is we could rotate this thing 8 times and it would still line up with itself. So this is called 8-fold rotational symmetry. Rotational symmetry. Now, this fold, don't be confused. It's not talking about like folding a piece of paper. It's fold meaning like how many times it has rotational symmetry. So, like if you scored a 20% on the first test and a 60% on the second test, that means you scored 3-fold more on the second test, so 3 times more. So the fold, don't be confused. That's not talking about actually folding this shape. It's talking about how many times it has rotational symmetry. Okay? And then another thing you'll be talking about with rotational symmetry is how many degrees do you rotate it each time. So if it has 8-fold rotational symmetry, that means we would rotate it, well, all the way around is 360 degrees. So each time you would rotate it 360 divided by 8. Oops, I'm sorry, that got kind of messy. So it'd be 360 divided by 8, which is 45 degrees. So each time you're turning this, you're turning it 45 degrees. Okay, and this shape, it has no symmetry. You can't turn it or reflect it so that it'll line up with itself. Okay, which of these shapes have reflectional symmetry, where we could draw a line of symmetry in there? It looks like this one would. It would have a line of symmetry right down the middle. And actually, it's going to have 5 lines of symmetry. 1, 2, 3, 4, and 5. So it's going to have 5 lines of symmetry on this one. This would have reflectional symmetry. This one here looks like it's going to have just 1 line of symmetry right down the middle. And then if we tried, doing it this way, that heart wouldn't work out. This one does not. It has rotational symmetry, but it doesn't have reflectional symmetry. Our butterfly is pretty darn symmetric. We would cut it right down the middle, and my line didn't go perfectly there. So this would be our line of symmetry. This wing matches up with this wing. Now it looks like it's maybe not perfectly symmetric, but the idea is that each half of the butterfly is pretty darn close. The mountain, if this lake were super still, you might have a line of symmetry right here where the mountain is reflecting onto the lake. And then the snowflake, it looks like we'd have 1 line of symmetry here, 1 down the middle, 1 diagonally, and then we're actually going to have a few more. We'd have 1 this way, 1 this way, and 1 straight across. So it looks like we got about 6 lines of symmetry. 1, 2, 3, 4, 5, 6. Yep, 6 lines of symmetry. And then the face of this primate, I'm guessing this would be our line of symmetry. The faces are pretty symmetric. Okay, and then lastly, which have rotational symmetry. Well, this one would have rotational symmetry. You could turn it 5 times before it got back to itself, and it would line up each time looking just like it did before. So this has rotational symmetry. We'll just make a little smiley face. This one does not have rotational symmetry because the heart would be upside down or to the side, so this one does not. This one we said does have rotational symmetry. It has 4-fold rotational symmetry. If this, once again, were a perfect reflecting mirror, it would have rotational symmetry because if you rotated it 180 degrees, the mountain would now be in the lake and it would look just like itself. This one does have rotational symmetry. It has 6-fold rotational symmetry. You could rotate it 1, 2, 3, 4, 5, 6 times around. And this one does not have rotational symmetry. Okay, lastly, there's a quick example of a symmetric face. So this guy's face is not very symmetric. You can see his hair is kind of one way. He's got a little mullet sticking out the side here. But what we've done is we've taken it and we made it symmetric. So what I did is I just cut it right down the middle, and then we took the left side and we reflected it to the right side, and now this guy looks much more handsome, and symmetric faces are very desirable. So typically people who are deemed very attractive, they have very symmetric faces. So he looks really good. He actually lost some weight by doing this. His hair looks a lot better this way. And then if we take the right side of his face, or I guess the left side of his face, what we see is his right, he's going to gain a bunch of weight. He's going to have a double mullet going on here. So the symmetry, not all faces are perfectly symmetric, but those who are symmetric typically are deemed a lot more attractive. So hopefully that helps you with polygons and symmetry.